All right, chemistry fans, here we go. We have one other real gas formula to go over, and that's the ideal gas law. And this is different, as you can see by our notes, that this one is different than a combined gas law. Remember, in a combined gas law, while you're really looking at three of the four factors that can affect gas behavior: pressure, volume, and temperature. It is always assumed in the combined gas law that the moles, the amount, is held constant, and so it's not part of the equation. But certainly you'll have situations where you could be putting gas into a container, taking gas out of a container, or something along that line that is going to affect the pressure, temperature, volume, and stuff. So you need another equation that includes the moles of a gas. And I also look at it this way: the combined gas law, you have a gas in one situation, you switch it to another. So it's a change from one set of conditions to another. With the ideal gas law, you can just go, hey, what's this gas going to be? What should I expect from this gas at this point here? So not a comparison, a single deal. And it includes the moles. So you can figure out directly how much gas, as opposed to that indirect going to STP volume kind of thing that we did yesterday. Okay. So first we got to look at amount and volume and invoke our friend Avogadro's name again, and then incorporate that into the gas law, which you can see right here. Here's what the gas law is: PV equals nRT, or some people just think in their head PIVNER to remember the formula. And we'll break it down as we go. But first, let's talk about Avogadro. Okay. When we looked at pressure, volume, pressure, temperature, and volume, temperature, the Boyles, Gay-Lussac, Charles law stuff, and jammed them all together into the combined gas law, the one thing that they had in common, which is true of the ideal gas law also, is that they were linear relationships. And that's not going to change. Here you can see Avogadro's law is comparing volume to number of moles you put in. Okay. And it's a direct relationship. It's a direct proportion, just like we saw with volume, temperature, and pressure and temperature. As you add more moles of gas, your volume's going to expand because you just got more. If you take out gas or have less, then it's going to be less. So they're proportional, and they all meet on this straight line here. So again, we're going to look at that math where, well, if they're directly proportional, I can change any proportion to an equality by multiplying it by a constant k. And what's that constant k? That's the slope of the line. Okay, so it really is following along the same stuff that we talked about yesterday. Okay, just a nice linear increase based on the number of moles. Okay, so let me get my face out of the way a little bit here. In the combined gas law, we did show you, we kind of walked through the algebra, that the proportional relationships were all linear. And so we can make them equal to a constant k. And we came up with PV over T equals k. And then we could do P1, V1, T1 equals P2, V2, T2 because they both had the same constant. Okay. And as we just saw with Avogadro's law, the volume is proportional to n, the number of moles. That's the letter they use for n. And so the volume then is equal to k times n, or if we rearrange for k, it's volume and n. Now compare that to what we already had here and stick it in there. Okay. That means with that direct relationship, just like pressure, temperature, volume, temperature, that moles is going to go on the bottom. So when I incorporate it in, that means that PV over NT is going to be equal to K, except for the ideal gas law, that constant number, they don't use the letter K, they use the capital letter R. And anywhere that you go in science, when you see a big R, it's the ideal gas constant. And it's just a number. And we'll see, it's just a number derived from putting values in for pressure, temperature, moles, and volume. and you figure out what that number is. Solve for R is basically it. Okay. So that's that. So that would be then PV over NT equals R, but then they rearrange it to kind of make it more in a straight line, not a PV over NT thing. And that's where PIV comes from. And just a reminder, P is the pressure. So atmospheres, kilopascals, things like that. V is the volume. N stands for moles. So don't forget, anytime a problem gives you grams, make sure you turn it to moles. Okay. R is just a constant number, the ideal gas constant, which we'll talk about in a minute. And T is just temperature. And again, we've said this all throughout gas laws, temperature will always be in Kelvin. Okay. So let's go through a couple of statements here that we know are true. The ideal gas law incorporates the amount in an equation so that all four factors affecting a gas are included. Since R is always a set number, then really what you're solving for is if you have any three or four variables, if you have pressure, volume, and temperature, you can find moles. If you have moles, temperature, and volume, you can find pressure and that kind of thing, because R is just a given number. So you can always solve for one of those variables if you're given the others. Okay. And what we're going to see after a couple days, really kind of maybe starting next week, is that because it includes moles, then this is the equation that we're using when we do stoichiometry with gases. But that's for the future. Okay. Now here's where does that number R come from? Well, the value of what the numbers, because we have two pressures we really use, atmospheres and kilopascals. The actual number is different for both because they're different pressure values. Okay. So it's based on the pressure used. Now, one thing to note, combined gas law, P1 V1 over T1 equals P2 V2 T2. It didn't matter, other than temperature, which always has to be in Kelvin, it didn't matter what, say, the volumes were in, V1 and V2, as long as they were the same. So as long as they were both milliliters or liters or kiloliters or gallons, it didn't matter. If they were different, then you got to change one to match the other. But that didn't matter. In the ideal gas law, because you're using this constant, this theoretical slope of the line kind of thing, then you pretty much have set variables for all. I mean, set, they have to be in a set unit. Now, temperature is always in Kelvin. N is always moles. You're going to see in a minute when I go to the next slide, volume is always liters. Okay. And then pressure is either atmospheres or kilopascals, and that will determine which number for R you use. Okay. So here we go. Let me move my, oops, I went one too far. I want to do a little review. We talked yesterday and did a problem, or we talked for a couple of days and did problems about standard conditions, standard temperature and pressure. Okay. And I just want to reiterate that because it's very important to figure out where R came from. Because the volume of the gas varies with pressure and temperature. We'll just use those, for example. There's a set of conditions, and these were really, again, back to Avogadro's basis for finding the moles with gases, and the equal volumes are have equal particles and stuff. That's what STP is, standard temperature pressure, the standard conditions. Standard pressure in our class is 1 atmosphere or 101.3 kDWB. Okay, there's other values for other pressure values out there, we don't care. Those are the two we stick to. Those are the two biggest you see in chemistry all the time. And standard temperature is 273 Kelvin, always. Okay. And this is just a picture before we get to R to show what that means about standard temperature and pressure and what Avogadro said and found the moles. You notice that you have 1 mole of 3 different gases here. They are at standard temperature, 273 Kelvin. They are at standard pressure, 1 atmosphere. And they always occupy 22.4 liters. That's the key, 1 mole of any. And we talked about this in finding the amount of moles with the combined gas law. 1 mole of any gas at STP will always, always, always occupy 22.4 liters of space. It was that discovery that really led Avogadro to figuring out the mole. Okay. So where does that play into calculating the value for R? Because then you plug into the ideal gas equation the values you know at standard temperature and pressure. Okay. So the volume, 1 mole of gas at standard temperature will always occupy 22.4 liters. Right? So if I want to solve for R here, then I'm going to get that number just based on which pressure unit I use. Do I plug in 1 atmosphere here and then solve for R, or do I plug in 101.3 kDWB? Okay. It doesn't matter, but you can see in the next 2 bullet points that if I put in 1 atmosphere along with the 22.4, the 1 mole, and 273, then R comes out to be 0.0821. Okay. So that's its value at standard temperature and pressure. And that's the value we use in the ideal gas equation if the pressure is in atmospheres. Okay. You can see by the next bullet here that if instead I put 101.3 kDWB in for pressure and the 22.4 liters and the 1 mole and the 273 Kelvin, then R turns out to be 8.314. So those are the 2 constant values you just get used to knowing because you do the problem, so they get stuck in your head as to what they are. Okay. But you'll use one of those, you'll use that number to plug in for R, either one depending on what the pressure value is. And then again, I put down at the bottom, your volume will always then be in liters. Amount will always be in moles, not grams, kilograms, anything else, always in moles. Temperature, always in Kelvin. And then you match the R to the appropriate pressure. 0.0821 for atmospheres or 8.314 for kilopascals. Okay? So let's take a minute. Is an ideal gas a real thing? No. The ideal gas is a laboratory theoretical. If gases were followed exactly what we think about gases and just whizzed around as independent little things bouncing around a container in straight lines, that'd be great. Okay, but they're not. Okay, real gases, there is, if they're flying by each other, they will have a bit of attraction and deflect that straight line. If they bounce into each other, they'll bounce off. That is true. So they're not completely, another part of that theory is if they bounce inside a container, they wouldn't lose any energy at all, 0. And that's not really true. Real gases, when the particles are flying near each other, they do kind of veer. If they bounce into each other or bounce into the walls of the container, they will lose a little bit, they will lose some energy. I mean, it just is what it is. But 9 times out of 10, and in most situations that you encounter, real gases behave in an ideal manner. And that's why we can use the gas laws to do all sorts of things. Fly hot air balloons, go into space, fly airplanes, submarines, scuba diving, all sorts of stuff, okay, that would involve gases. Because most of the time in our world that you and I and chemists work with, real gases behave like theoretical ideal gases. The only 2 exceptions are at low temperature and high pressure, because if you think about it, at low temperature and or high pressure, it's really condensing those gas molecules towards that liquid phase. And then the closer they get, the less they behave in an ideal fashion. So at very low temperatures and high pressures, then our gas calculations with the gas laws wouldn't work. But we won't have to worry about that. But that's just something you should understand. Okay, so let's walk through an example. And then tomorrow, much like today's, Wednesday's homework, I'll just do a couple more examples and give you a worksheet to go through. After this one, you'll have another one of those short little quizzes. Anyhow, so here we go. You have a gas, nitrogen by the way. You have nitrogen gas at 25 degrees Celsius that occupies 15 liters at a pressure of 1.75 atmospheres. And it wants to know how many grams of gas this is. And your equation is Pivner, PV equals nRT, okay? First thing is figure out what you have for values. Your pressure is 1.75 atmospheres. And since it's in atmospheres, that's good. Your volume is 15 liters, and volume always has to be in liters, so that's good. N is what you're looking for because N is moles. And if I know moles, I can go to grams. So anytime it talks about grams or anything like that, you've got to change any grams to moles, or if you find the moles, turn it to grams, whatever. Anything revolving grams is moles. Okay. And honestly, the biggest error in these problems, most of the time, is people solve for N and forget that it's moles and don't convert it and leave it there and call that grams, and then they're wrong. The R in this case is we're going to use the 0.0821 number because that's the one that matches with atmospheres. And then the temperature was 25 degrees, but remember we have to be in Kelvin, so add 273 and it's 298 Kelvin. So now I've got all my numbers placed where they should be. It's plug and chug. Okay. You're going to plug it in, you're going to solve for N, and then you're going to change that back to grams. All right, so what does that look like? Well, there it is. Our pressure, our volume, our N is what's left over. There's our R. That's our gas constant, and there's the temperature. And I just solve for N. And in doing so, what I'm going to see is the atmospheres cancel, because this big, ugly mess behind the 0.0821 is the actual units that number would have. Okay, atmospheres cancel, liters cancel, kelvins cancel. I'm left in moles. When I get all the mathematics done and solve for N, you should get about a little over almost 1.1 moles. But again, that's moles, not grams. So to get to grams, I need to multiply by the molar mass. And don't forget that nitrogen is diatomic. And so that's about 30 grams. Okay. That's basically it. It's not a whole lot different than the combined gas law. It's really just figure out the values, plug them in, make sure you have things in the proper units, and plug and chug. Anyhow, there will be a little short quiz after this. So enjoy, stay healthy, and we will talk to you soon, chemistry folks.